Hello. I'd like to do an addendum to the review of complex numbers that I did in video 8C because there's some problems that have come up that some of the students need to be able to work with the complex numbers in a rectangular format rather than converting them over to a polar format before you do a multiply and divide. And I want to point these techniques out to you real quick. To start out here, if you take a look at this example, I have a J4 times the quantity 3 plus J5. Now most of you most likely, because it's a multiplication problem here, would convert this J4 to a 4 at an angle of 90 degrees, and you'd convert this 3 plus J5 to a polar form. You'd multiply the two together by multiplying the magnitudes and algebraically adding the angles to get a polar form. And then you'd convert it back to rectangular if you wanted your answer to be in rectangular form. Take a look at this problem here. In this problem here, you'd convert this rectangular form to polar form. You'd convert this rectangular to polar form. You'd multiply them out. You'd take this to rectangular form to polar form, this rectangular form to polar form. You'd multiply them out, and then you'd have to convert both of the polar forms here back to rectangular so you could add them. That's a lot of rectangular to polar and polar to rectangular. So let me show you how you can do some of this multiplication and division by keeping it in rectangular form. And you're going to have to remember, in a previous math class, you probably had I as the complex number, the square root of minus 1. Well, we can't use I, in engineering, so we have to use J. I is current. So our complex variable is going to be J, and J is equal to the square root of minus 1. J squared, therefore, is equal to a minus 1. J to the third is equal to J squared times J, which is simply a minus J. And J to the fourth is equal to J squared times J squared, which gives us a plus 1. So we're going to use some of these in the mathematics, and what I mean by that is, let's say as an example, you were doing a nodal analysis problem, which you will be doing incidentally coming up in the next lecture, where you're going to have your first level equation looking like this. I1 plus I2 minus I3 equals 0. When you go to your second level equation, let's say you got 24 minus V1 over 2 plus the quantity 12 minus V1 over a J2, and that's not J squared, it's J2, minus V1 over 4 equals 0. And how could we, rather than converting everything here to polar and polar and polar and polar just to divide those out, let's find a least common denominator here. And this is the way you'll most likely work these problems. We're going to find a least common denominator. In terms of the integer, it's a 4, and the J, so it's a J4. So the least common denominator here is a J4. So I'm going to multiply each of these quantities by a J4, and I do here, I do here, I do here, and I do over here. So if you take a look, this 2 goes into that 4, and I get a J2 up here, and I take a J2 times a 24, and I get a J48. And I take a J2 times a minus V1, I get a minus J2 V1. And over here, the J's cancel, and the 2 goes into the 4 2 times, and I get 2 times a 12, which is a 24, and a 2 times a minus V1, which is a minus 2 V1. And over here, the 4's cancel, and I simply get a minus JV1 equals 0. I clean all this up, and I want you to notice that I get the whole way down to here, and to this point, and I've never went to polar form yet. I kept everything in rectangular form. Now at this point, I see that I want to come up with the voltage V1, and I want to do a division problem here. So the way I'm going to work this out, I could multiply the top and the bottom by the complex conjugate. That would solve this. I can multiply the bottom here by 2 minus J3 and the numerator by 2 minus J3. And it would, but eventually when I do that, I'm going to have to convert this back to polar. So why not do it individually here? And I do that, and I end up with my V1 equal 14.9 at an angle of 7.13 degrees in volts. And you can see I can convert this very easily over to from the frequency domain to the time domain. We've done that many times. Let's take a look at another example. Let's say you're going to be doing Kirchhoff's voltage law, and you will be in some loop analysis coming up here. And let's say you get the first level equation that looks like this. Plus V1 plus V2 plus V3 equals Vt. And the second level equation yields 3 minus J4 over 2 plus J5 over 4 plus the quantity 5 plus J2 divided by a J2. And again, that's not J squared, it's J2, equals the total voltage. You get a least common denominator here, and the least common denominator in this case is going to turn out to be equal to a J4. I'm multiplying each of these quantities by J4. Now let's clean this up and see what we get. We take this 2 goes into this 4, results in a 2, and you have a J2. You have a J2 times a 3, you get a plus J6. You have a J2 times a minus J4. The J times a J is the minus 1. It takes care of that minus 1. You end up with a plus 8. Make sure you see that. Over here, the 4 cancels with the 4, and you have a J times a J5, which gives us a minus 5. Make sure you see that. And over here, simply the J's cancel. And 2 goes into 4 twice, and you get 2 times 5, which is a 10. And 2 times a J2, which is a J4. And at this side, it's just a J4 Vt. Cleaning this up in terms of Vt, I get the whole way down to this point, and I have not used polar form yet. Everything's still in rectangular form. Now I can convert this at this point to polar and this to polar. This denominator is just going to be 4 at an angle of 90 degrees. But notice I could multiply the top by a J4 and the bottom by a J4, like I did down here. If I do that, I end up with a minus 16 in the denominator. The J times a J is a minus 1. The 4 times a 4 is a 16. And I expand this numerator out, and I get a minus 40 plus J 52. I take the minus 16 into each of these quantities here, and here's my phasor voltage. The whole way down to this point here, 2.5 minus J, 3.25. Work the whole way down to here on this circuit analysis problem with complex numbers. Did not use polar form yet. Now I go to polar form. The only reason to go into polar form is because we want to go from the frequency domain to the time domain. You have to get this in this polar form. You have to get it in the frequency domain form so you can get it to the time domain. And that's what I did. Now, understanding those techniques, let's go back here. Let's take a look at these two problems I started out with. Instead of converting this to polar and converting this to polar, multiplying them out and going back to rectangular form, let's keep everything in rectangular form. And you'll know when you'll know in your particular problem when you want to keep something in rectangular form. I mean, impedance, most of the time, to get something practical out of the impedance, you have to get it in rectangular form, because you can extract the real part and the reactive part, the imaginary part, which is the reactive component. But if you're going to use impedance in an Ohm's law equation to multiply or divide, you want to get into polar form. So you'll know when to keep it into rectangular form. But let's do that. Let's do it down here. Here's the original problem. Let's just take the J4 times a 3, and you get a plus J12. And take the J4 times a J5, you get a minus 20. You're done. You kept it in polar, you kept it in rectangular form. You'd still be messing around converting this to polar form back here so you could get everything back to rectangular. So we kept everything in rectangular form. How about this problem up here? Let's keep everything in rectangular form because you're going to add them anyhow. So if you look down here, that's exactly what we did. We took a 3 plus J3 times a 5 plus J2. We multiplied the 2 times a 5, you got a 10. The 2 times a J2, you get a plus J4. You have a J3 times a 5, you get a plus J15. And a plus J3 times a plus J2 is a minus 6. You clean all that up, and you get your 4 plus J19 for this. Kept it all in rectangular form for this. Working this here. Let's go over here. Here we have the second part of that. We take the 5 times the 6, you get a 30. You take the 5 times the minus J2, you get a minus J10. You take the J3 times the 6, you get a plus J18. And you take a J3 times a plus J2, you get a plus 6. You clean that all up, you get a 36 plus J8. You add those two together, and you get your 40 plus J27. You didn't have to use polar notation at all to go from this expression down to this expression. Now, if you change that to polar, and you change that to polar, and you multiplied them, you change that to polar, and you change that to polar, and you multiplied them, then you converted this back to rectangular, converted this back to rectangular, so you can add them, you're going to get that same answer. But I think you'll agree this is a lot easier. So these techniques, I hope they help you in your loop analysis and nodal analysis of sinusoidal analysis of sinusoidal circuits. And all we did was use the j as the complex variable square root of -1, and we remembered that j squared was a -1. J to the third is a minus j, and we probably won't be multiplying. We won't get to the j to the fourth, but if you ended up with the j to the fourth, you're going to see it's simply a +1. And that concludes this amendment to the video 8 Charlie.